Oh, yeah, sure.
If I use AI to make my flight. This one is entirely human created.
It was created a couple of years ago.
Yeah, that's right.
I think I heard this last one.
Oh, yeah, sorry. That's correct. Needs post processing. Yeah. To make content for the slides, and then I have polished slides. The output is what you can. Who output? What we did was this paper with O that I was talking about. He actually put this into notebook elements and said, generate a video explaining this stuff.
Oh, I saw this. I think you shared it or something.
Yeah, yeah. And glory. It got the algorithm right.
Recording your talk.
It's on, right?
Wait a couple of minutes.
Sure. Sounds good. Are all the seminars 90 minutes or is it, that's the norm?
Yeah, the ICTS norm is 1.5
Yeah.
hours.
Yeah.
Yeah, good afternoon. Thank you all for coming. Yeah, maybe I should introduce myself first. I'm Jayakumar Radhakrishnan. I'm a faculty member at ICTS. Yeah, but we are all here for, we're very happy to have Professor Vinod Vaikuntanathan from MIT. He's the Ford Foundation Professor of Engineering at MIT's EECS department and a principal investigator at the MIT Computer Science and AI Lab. Vinod got his BTech in computer science from IIT Madras in 2003 and his PhD from MIT in 2009. Vinod's contributions in research and mentoring have been recognized by several awards, including the Gödel Prize for constructing efficient, fully homomorphic encryption. Vinod is a leading authority on cryptography, especially lattice-based cryptography, one of the topics of his talk today. So yeah, welcome, Vinod. We look forward. Thank you.
All right. Thank you for the kind introduction, Jayakumar, and thanks for the invitation, Rajesh and Jayakumar. It's a pleasure to be here. I've been having fun sort of, walking around your beautiful campus. Pretty fun. So I'd like to tell you about something that I've been thinking about for the last 15, 16, 17, some number of years, which is integer lattices and its connection to the field of cryptography. Now, I realize that a lot of these words and terms might be a little bit out of distribution for many of you here. And for that, and in general, that reason and in general, please feel free to interrupt me with questions. I love questions. The thing that I dread the most is not getting any questions from the audience. Yeah? So ground rules clear? Great, wonderful. So let's get into it. So let me start with the party trick. Okay, so here are two probability distributions, point clouds that I've drawn. It's a 2D distributions, right? On the left is a Gaussian distribution, so you can sort of see. On the right is a distribution called the pancake distribution, which is basically take a Gaussian distribution and take your nails and kind of, draw out, a portion, right? Another way to see it is that it looks like a bunch of pancakes, sort of, in parallel, right? Another way to see it more technically is that it's a mixture of Gaussians. So each of these is a tiny Gaussian, and what you have is a mixture of many Gaussians, right? So many ways of thinking about it, but for the moment, just think about the picture. Now, if I show you one picture versus the other without the label, can you tell which one is which? If I let's say I described what pancake is and what Gaussian is, I hit the labels and I showed you this picture. Can you tell which one it is? Of course, yes, right? It's obvious, right? Well, now let's go up one dimension, okay? One of these is the pancake distribution, and the other one is the Gaussian point cloud, okay, without any apparent structure. Which one is which? Can I get takers for, can everybody see actually? It's more or less visible, right?
This is a section. What is this? It's a cross section of.
So this is, I'm viewing the 3D point cloud from one angle. That's it, right? So it's either a Gaussian point cloud or a pancake point cloud, but I'm viewing it from one direction. Here's what it looks like.
It's projected onto a plane.
Projected onto a plane, exactly, precisely. Some plane. Can you tell which one is the point cloud and which one is the Gaussian and which one is a pancake? seems hard, right? I mean, it seems hard because I'm looking at it from the wrong angle. So let me help you out a little bit. So let me rotate these point clouds, right? Do you see? Yeah. So you know, the difficulty is that I am sort of viewing it as a two-dimensional entity. To do that, I have to project, and I'm projecting it onto the wrong plane, and I'm not seeing the structure. But if I do look at it from the right way, I do see the structure, right? So this is going to be a protagonist of today's show. I will actually put this aside for the moment, and he will come back. You know, this guy will come back later on in the talk, right? And in any case, this is called the Gaussian pancake problem for obvious reasons. So the problem of distinguishing between these two point clouds, given many samples from it. Yeah, so all clear? Good. Okay, so now let me change the topics a little bit. And I promised you that what I'm going to tell you here is very closely connected to the Gaussian pancake problem, but you won't see it until the end of the talk. So, you know, the other protagonist of this talk, in fact, the main protagonist of this talk is lattices. So these are periodic grid of points. Another way to see it is that, you know, they are discrete additive subsets of z to the n. Here it's z squared, right? Yeah, so they're discrete, clearly. They're additively closed because you take any 2 points and sum them together, you get a third point, or difference, you get a third point. Yeah, another explicit way to describe this is using bases, right? You take 2 vectors in R squared here, take all integer linear combinations of these vectors, you get a lattice, right? Differently from a vector space where you take all real valued linear combinations. Now, yeah, this is what it is. That's an n-dimensional lattice, all integer linear combinations of n linearly independent vectors. Yeah. Can see, okay, so I'm going to, yes, it's cryptographically hard to figure it out if I obstruct it, I guess. Yeah, is it visible, everybody? Yeah, okay. All right. So one sort of interesting fact about lattices is that the same lattice, namely the same set of points in space, can be generated by multiple different bases. So what you saw before was one possible basis that generated this set of points. Here is another basis. And you can draw it out and it'll generate the, in fact, this is not the only one. There are infinitely many bases for the same lattice. Some bases are prettier than others, and some bases are more useful than others. So intuitively, it seems, at least to me, that this basis is nice and round and pretty, whereas this guy is much less so. And in fact, this is borne out in a computational sense. Something to keep in mind. Yeah, so same lattice, it can be infinitely many bases. So lattices have existed in mathematics for, I guess, centuries. I guess a classical example where lattices come up is in the problem of sphere packing, right? So this is a question of, you know, what is the best way you can arrange oranges? What is the densest way you can arrange oranges in a given volume of space, I guess, right? So Kepler conjectured that the face-centered cubic lattice, which is sort of like this, is the densest sphere packing in 3 dimensions. Now, Gauss proved that FCC, the face-centered cubic lattice, which is basically you take this lattice and you put an orange with the center at each of these lattice points. He proved that this is the best lattice packing, in the sense that if you constrain your packing to put an orange on the on a lattice point, some underlying lattice, then the best you can do is a face-centered cubic lattice. But it could be that there are other ways of packing which have nothing to do with lattices that do better. In fact, this century, actually last century, a few decades ago, Thomas Hales proved that, in fact, that is not the case. FCC is the best packing, period. Right? So this is a very sort of it's a problem that I can explain to my 7-year-old, right? And she'll understand the problem. She will not even understand the things that I'm saying here, but they have very deep connections to lattices. Now, you could say, why live in 3 dimensions? That should be familiar to many of you here. 4, 5, how about higher dimensions? The exact answer here is, believe it or not, only known for dimensions 1, 2, and 3, which was known for a long time, and 8 and 24. And 8 and 24 was a work of Marina Vyazovska, which won her the Fields Medal a few years ago. right? So these are all lattice packings. In 8 and 24 is the E8 lattice and the Leech lattice that give you the best packings. Okay, so that's mathematics. Another example of where lattices come up in mathematics is what's called the Minkowski convex body theorem, which relates two quantities related to a lattice. One is the shortest vector in a lattice. And what is the shortest vector in a lattice? It is, lattice has many vectors. 0 is always in the lattice, but that's uninteresting, right? Give me the shortest in the Euclidean distance sense, vector, non-zero vector in the lattice. So that's the SH of L. He showed that this is tightly related to the volume of the lattice. The determinant of a lattice measures the volume, how dense the lattice points are packed. These quantities are related. The details are not super important right now. But this sort of happened in the early 1900s. And by the way, this is the same Minkowski that the physicists in the audience would know. It's a multifaceted person, I suppose. So that discovery and its applications led to an entire field called geometry of numbers, right? So lattices are clearly geometric objects. They're also number theoretic objects because you're dealing with integer points, really, right?
Sir, what are we learning about?
It's not from God. It's okay, I got it. Okay, I see. So what are we learning about? We are learning about lattices. And we're learning about cryptography and how do you do cryptography with lattices. In fact, what is cryptography? Does that answer the question? Sort of? I will take it as yes. All right, okay. So, so lattices have been used to prove many number theoretic facts. For example, quadratic reciprocity, if you have heard about it, is quadratic reciprocity theorem is a basic theorem that's in some sense is a foundation of sort of like Langland's program and other sort of deep things. Proof of quadratic reciprocity theorem follows from Minkowski's theorem. Right? So it's a number theoretic fact that is proved using a geometric fact. So that's mathematics. I'm a computer scientist, so let me sort of pivot a little bit into computer science. An example of where lattices come up in computer science is this problem of integer programming. Just to kind of calibrate myself, how many of you have heard the name integer programming? Know the definition? Okay, good. So it's really the following question, right? I mean, I'm giving you many inequalities in n variables. Here there are 2 variables and 3 inequalities. I should go. Okay, all right, good. So 3 inequalities, right? And these 3 inequalities define a space.
Sorry.
Oh, okay, all right. It's all right. I from time to time, if I'm reminded of the existence of God, it's not a bad thing. Not a bad thing. All right. So you have 3 inequalities, right? They define 3 hyperplanes, right? And points satisfying these inequalities live here, right? In this intersection of hyperplanes. And the problem of finding a point in the intersection is linear programming, essentially. Problem of finding an integer point in the intersection is integer programming. Right, that's integer programming. Now, there's a big difference between how difficult it is to solve linear programs versus how difficult it is to solve integer programs. Linear programs can be solved in what's called polynomial time, so pretty fast. In fact, we can do it quite routinely. Integer programming is known to be NP-complete, which means we expect that there are no polynomial time feasible algorithms that solve integer programs in general. Right? Now, yeah, so this is find an integer point in the convex body. Good. So what does this have to do with lattices? I mean, there's clearly some lattices showing up, right? I mean, integer points are sort of a lattice. But another way to do it is to say, another way to see it is to say, well, let's actually try to make this ugly looking convex body nicer by doing a linear transformation. Okay, so it turns out that there's this thing called the Fritz-John theorem, which says that you can do a linear transformation to any convex body so that it looks roundish. What do I mean by roundish? You can look at the largest sphere that you can inscribe within this body and the largest circumscribing sphere. Their radii are not too far apart. In fact, they are a root n far apart, and that's what Fritz-John theorem says. And that can be done. You can take any convex body, do a linear transformation, you can get this nice roundish convex body. But of course, if you do that, you have to also do the linear transformation on the set of integers, right? And what does that give you? That gives you a lattice. A lattice is by definition a linear transformation applied to z squared, the set of all integer points, right? Not very hard to see. So again, we just transformed the problem to look at a nicer convex body, but now you have to look at lattice points instead of z squared. Okay, it still doesn't seem to have made things any easier. So how do I go about finding finding a lattice point inside this nicer convex body? One way to do this is to say, well, let me look at all points in the sort of the hyperplane spanned by B1, right? So all multiples of B1, really. Then let me look at all points of the form integer times B1 plus B2. So that's basically a shifted hyperplane. And then keep going, a few steps so that I cover the whole convex body and hopefully I find an integer point inside the convex body, right? So I can do this, right? But what happens if you use a bad basis of this kind? A bad basis is one where the basis vectors are close to each other. Another way to see it is that the Gram-Schmidt vector here, or the distance between these hyperplanes, is very small. What does that mean? That means that the number of hyperplanes I need to look at to cover the entire width of the convex body is very large, right? And that will be the case, and you won't really get a very good feasible solution. So Ravi Kannan observed, a computer scientist, who some of you may know, observed that one way to make progress on this is to take the basis that you're given and transform it into a nicer basis, right, which looks more brownish, I guess, and then do the same strategy. It turns out that for an appropriate notion of nice basis, you just need to, in each direction, you just need to look at root dimension convex, root dimension hyperplanes. And that immediately, and there are constant number of dimensions, let's say, and that gives you a constant polynomial time algorithm. Yes?
One for making the convex this region roundish, and then one for.
Good. Yes, I am, right? So one transformation did the same thing to both the convex body and the lattice, right? And the other one just found a different basis for the same lattice. Right, so they are both linear transformations because going from one basis to the other is also a unimodular linear transformation, but whatever, yeah. Exactly, precisely. Right, so he could make this strategy work and get the first solution to integer programming in a constant number of variables, with a constant number of variables. Why a constant number of variables? Because in each direction, you have to look at root dimension of the space many points to the power, the number of variables, unless the number of variables is constant, you're not going to get a polynomial time algorithm. And so he did this. So he wanted a way, yeah, Rajesh.
Does it depend on, I mean, here you have like a triangle.
Yes.
But as you increase say, if you have a polygon of many inequalities, is there any qualitative change?
Good. So the whole point here of this algorithm is that the dependence on the number of inequalities is polynomial. So let's say there are n variables and m inequalities. M could be much larger than n in general, right? The dependence is something like m to the power n. So the thing that really makes you work super hard is n. And as long as that is a constant, let's say 2 or 3 or 5 or something, it doesn't matter how many inequalities you have. You could have a very complex polygon. It doesn't matter. Great question. Yes. Yes. Sorry, can you say again one more time? Yes. Yes, that's correct. Exactly, precisely, right? So the problem size is the number of variables and the number of equations, right? So think about the setting where the number of variables is equal to the number of equations, roughly. I don't know how to, yeah. So this seems like a special case, but it was already extremely useful. People didn't think that this could be solvable. Yes.
That region bounded by these inequalities is sufficiently big, then you know there will be a lattice.
Good. Excellent. Excellent. That follows from essentially Minkowski type arguments. The question is to find it. So the question is to find it efficiently. By efficiently, I mean in time polynomial in the dimension of the space and really the input length, right? Yeah. Correct. Yeah, that's right. So I have to make it clear that these two statements that I'm saying do not contradict each other. One statement that I said is integer programming is NP complete. The other statement is Kannan actually found a polynomial time algorithm for it. So what's the difference? It's polynomial in the number of inequalities and not polynomial in the number of variables. Right? That's That's the M to the N, right? So they are both correct, the two statements.
So finding a point as well as seeing if there is an integer point inside this region.
Yeah.
Those are equivalent, like self-reduction in P.
That should be true. I don't know if that exact statement is true or not, but it should be somehow.
Incomplete problem.
Yeah, it's search and decision is, but
The comment there was existence of a point under an assumption that the volume is sufficiently large.
Yeah.
So then we override these two statements.
so let me just say, what is Minkowski's theorem? At the end of the day, it's pigeonhole principle, right? You say there is a sufficiently large volume, right? And there ought to be sort of 2 points in the lattice that collide, and then their difference is a non-zero lattice point, something like that, right? But pigeonhole principle does not give an efficient procedure to find the object, and that is what I care about.
What about something intermediate, like if we just want to not find the point, but know how many points?
So even the decision problem of, let me think if I'm saying this correctly. I think counting the number of points is also hard. In fact, it may be even harder than NP, like Sharpie hard, potentially. I'm not exactly sure. Yeah, so all these variants turn out to be pretty hard. Okay, so to make Kanan's algorithm work, he needed a good basis, right? And the way, and the sort of the notion of good basis that he used, he didn't need a good basis to exist. He actually needed to find it in polynomial time. What is the algorithm that found a good basis? That is the Lenstra and Lovasz algorithm. I just heard, an hour ago that LLL is used in cosmology somehow, right? Which is like blows my mind. LLL finds the shortest vector and the short basis of any lattice, of any constant dimensional lattice in polynomial time. And if you put it together with Kanan's idea, you get a polynomial time algorithm for linear integer programming.
This preceded Kanan's algorithm?
Yes, this preceded Kanan's algorithm, and Kanan sort of looked at it and said, oh, I can use it with my idea to solve integer programming. Exactly. Okay, so we'll see a little bit about LLL in a minute. Yes. So this idea, you mean, the Kanan idea of sort of like covering things and so forth. I think so. I don't know if anybody has really bothered to look at not convex sets. Although like I am not, I don't know. Yeah. All sorts of weird things happen if you don't have convexity. Okay, so this all gave you an algorithm to find short vectors, short bases, integer programming with a constant number of variables or constant dimensions, right? But really, again, what I would talk about for the rest of this talk is lattices in n dimensions, huge n dimensions. And I want things to be either polynomial time, or when they are not polynomial time, I want to use things and so forth. So n dimensions, n being very large, right? So now there are problems that are very simply defined, but they turn out to be very hard. One example is the shortest vector problem. So I give you a basis of a lattice. Find me the shortest vector in the lattice. And of course, I think some of you may be thinking 0 is a vector in the lattice. I'm not interested, thank you. I want a shortest non-zero vector. So that's the shortest vector problem. Another problem you could care about is the closest vector problem. So I again give you a basis of a lattice, and I give you a target vector, some point in R to the n, and you give me the closest lattice vector to it. That's the closest vector problem. And of course, you could think about approximate versions of it. So, maybe I would say I'll give you a basis. You don't have to give me the shortest lattice vector. Give me something that is at most 100 times bigger than the shortest lattice vector. So that's the approximate shortest vector problem. Alpha here is the approximation factor, so like 100 here. Right? So these are all problems that one could care about in large dimensional lattices. And these problems all turn out to be very, very hard, as we'll see in a minute. Okay, so LLL actually gave you a much more general thing. It actually gave you an algorithm to find the shortest vector and short vectors and short bases in n-dimensional lattices, except when n grew, all they could find is a 2 to the n over 2 approximate shortest vector in polynomial time. Okay, so all I give you is polynomial time, and I say, well, do whatever you can. If you can find me the shortest vector, give it to me. But they couldn't, and nobody since then has been able to do that. The best they could find is a square root of 2 to the n approximate shortest vector.
So,
yes?
You said by a factor of 2 to the n.
By a factor of 2 to the n. So multiplicator. Indeed, indeed, indeed. That sounds terrible, right? That sounds really terrible. You know, I would agree with you, except this LLL algorithm had remarkable consequences. Even with this 2 to the n over 2 approximation, remarkable consequences. The thing to observe is that the approximation factor depends only on the dimension. It's independent of the bit length of the numbers that you know, I could give you a pretty nasty basis with n to the 500 bits of precision or whatever, right? Doesn't matter. It's polynomial in all of that. The approximation factor depends only on the dimension. So that already solved a whole bunch of problems. In fact, factoring polynomials over the rationals used to be an open problem at that point. LLL just kills it completely, turns out. In fact, the LLL paper was their first application was factoring polynomials over the rationals in polynomial time. It has many other sort of applications. Number theory, for example, you know, the problem of factoring a number which is a product of two very large primes, I'm thinking 500,000 digit primes, is a hard problem. But with LLL, I can actually find the factors when I tell you also a few bits of the factor. So I tell you p times q, but I also tell you maybe the half of the bits of p and half of the bits of q. Now it becomes easy. Now that didn't reduce the problem size by too much because there's still 250 plus 250 bits that you don't know. It doesn't matter. You can actually, LLL can actually find it. That was remarkable. And more generally, there's this meta theorem that LLL, if you don't think about your cryptography or your crypto system very carefully, LLL will break it. So it used to be that, well, I guess I wasn't around in the 90s. Well, I guess I wasn't sentient in the 90s, but you know, the story is that you know, people used to give talks constructing new cryptography in conferences. And by the end of the day, Don Coppersmith or Adisha Mayer, some mathematicians, they would have used LLL to break your system. Sometimes even online. During the talk, by the end of the talk, the thing is broken. Right? This is a remarkably powerful object, even despite the 2 to the n over 2 approximation. And so that's LLL. But the fact of the matter is, as Roger said, it is only a 2 to the n over 2 approximation, right? And that is more or less the best state of the art from 1984 until today. People have made slight progress, but nothing to write home about. Okay, so in other words, there is a curse of dimensionality here, right? In polynomial time, you can only find 2 to the n or 2 to the n over 2 or whatever approximation, right? On the other hand, if you want to find the exact shortest vector, the best algorithms we know run in 2 to the n time. So there's a bit of a trade-off here, right? So that I can find alpha approximate solutions in roughly this much time. You don't need to parse this exactly, but there is a trade-off between, as you increase alpha, the runtime decreases, right? And with these two extreme points. And that is the best known at this point. In fact, just to jump ahead, let me tell you that the security of everything that you do on your phones, on your internet, or whatever, is going to rest on the assumption that this is the best algorithm, period, for finding shortest vectors in lattices. And that's because all your phones are going to run lattice-based crypto systems in a few years, give or take 2, 3, maybe 4 years. So this is very important for us to really sort of understand, is this really the truth or not? Handful of people are thinking about it, but I think it should be more than a handful, really. Okay, so this is curse of dimensionality, right? Yeah, I don't care about graphs. Okay, so for those of you who care about quantum algorithms, even with quantum algorithms, we haven't broken this barrier. This seems to be the case. In other words, finding exact shortest vectors still seem to take time, 2 to the n. Grover's search can shave off from 2 to the n, you can go to 2 to the n over 2, but thank you very much, I'm not interested, right? Okay, so there's a curse of dimensionality sort of phenomenon happening. And that should make people, computer scientists who do who make their living finding efficient algorithms, polynomial time algorithms, sad. Here's a problem that has resisted attack for 40 plus years. But then there's a special breed of people, of which I am a member, who delight in hard problems, computationally hard problems. Also other hard problems, but yeah. And these are cryptographers. So we love hard problems. Why do we love hard problems? Because we want to design, engineer systems where it is an adversary, an attacker, that has to solve the hard problem. And my task is just to solve some easy problem. For example, in some sort of secure communication scheme, one example we'll see soon, my task would be to multiply numbers, two very large numbers. Anybody can do it with a computer, right? And the adversary's job, I'll engineer it so that to break the system, they would have to factor the number into its components. And that's extremely hard, as far as we know. Not with quantum, but it is hard, right? So that's what we want. We want to use this computational asymmetry in a way that creates a pair of problems. The task of the good guys would be to solve the easy problem, multiplication in this case, and the task of the bad guys would be to solve the hard problem. That's how we want to. Okay, so I imagine that cryptography is alien to most of you. So I want to spend about 5 slides telling you what happened in cryptography for roughly 3,500 years. Okay, ready for it? Okay, great. Okay, let's try. Okay, so here's a canonical problem in cryptography. It's called secure communication. And imagine sort of Roman generals, right? I mean, Roman general trying to send a message to his minions. And there's a messenger carrying it, right? And the question is, what happens if the messenger is captured, right? Can someone open the scroll and actually read what is written there? Ideally not. The general would want to encode or encrypt this message so that even if the messenger gets captured, all that the enemy sees is gibberish. Okay. So that's what you want. And in the modern context, there are no Roman generals, there are no minions. Instead, there is you trying to buy something from Amazon. Okay, these are two parties, right? And they want to send messages back and forth. In the middle lives internet routers. Heaven knows what goes on there. People might capture your packets or whatever, right? And you still want security. Okay. Let's sort of, we like to, in cryptography, we like to think about these little people, right? Alice and Bob, we call them, right? And Eve, this nasty looking being, right? So there's Alice and Bob. Alice has a message M, could be a bit, could be a number, string, whatever you want. She wants to send to Bob through this public channel that the eavesdropper Eve can observe, really, right? Now, we could say the eavesdropper might actually be able to do more than observe, but let's keep things PG-13 here for the moment. All right, so without any setup, can you solve this problem? Can Alice really communicate to Bob? So Bob knows what Alice is saying, but Eve doesn't. Can you actually do this? How many people are optimistic about the possibility? Wow, I have a bunch of pessimists in this room. It doesn't bode well for me. No, there's nothing. This is it. This is a public channel. That's it. Whatever goes through here, Bob can read, and this person can read as well. What does the room think? Well, I already said it, right? Whatever goes through this channel, Bob can read, and so can Eve, and they have the same information, they have the same computational power, so Eve can run whatever algorithm Bob runs to get whatever he gets, right? So there's no asymmetry here, really. So one way to solve this problem is to give Alice and Bob a key K, which could be a sequence of numbers, bits, whatever, right? That they know, but Eve doesn't. Now, how do they come up with this secret number? That's a topic for another day. For a moment, think about Alice and Bob huddling in one room, and they're writing this sort of a sequence of numbers in a piece of paper. They keep it secret, and that's that. So now you have asymmetry between Bob and Eve that you can use to do secure communication. And people have done this, so I guess the Romans did it, back in the days. So for example, the key K is a number between 0 and 25, right? And to encrypt a sequence, you just shift it by K letters, This is what I teach in my, this is what I actually taught in my Cambridge Math Circle lecture to 7-year-olds. And they love it. They love the notion that they can talk to their sibling without their parents listening up. It's a major hit. Yeah, so this is what happens, right? I mean, you shift by 3, C becomes F, R becomes U, et cetera, and going back, if you know the key, you can go back. Now, you might think this is pretty silly, right? I mean, because I can enumerate over all 26 possibilities of the key, and Eve can go back as well. It takes about 26 times more time, but come on, 26 is a small number. In any case, this is encryption. Going from plain text to ciphertext is encryption. Going back is decryption. So, this can be broken. In fact, you can go to this website. It's a very nice sort of like visual illustration of how to sort of break this stuff. Yes? 26 factorial. Okay, very good. Very good. That's it. That's great, right? And what you're describing is called a one-time pad. So that actually is a secure system with one catch, right? So do you want to, map, no. So what you're saying may not actually work, right? Because a C, in what you're saying, a C is always mapped to a Z, if you want, right? So what you can now do is a frequency analysis attack. In fact, if you go to this website, that does precisely that. And that sort of observes that, E is the most frequent. If you know, the thing is English. E is the most frequent character. Now I go and see what is the most frequent character. I know that that's E, and I can pray. The thing that is actually secure is if you use a different random shift for each position of the text. Then it really becomes truly random, right? The ciphertext becomes truly random. That's called the one-time pad, and yeah, people use it. Okay. In any case, many historical encryption schemes, what you described is called a substitution cipher, right? That can be broken. Many can be broken by hand, if not, like a computer do it. So that was the case for a long time, and there's a whole story of how the Germans used the Enigma machines in World War II, and how the British, including Alan Turing, sort of broke it, and so on and so forth. So these were, I would still consider them fairly primitive sort of encryption systems. So things really kind of changed in the 1950s and 60s and 70s, and really 70s, where people started using hard mathematical problems, computationally hard mathematical problems, to design crypto systems, with the idea that somehow encrypting should be the task of solving an easy problem, and the inverse problem should be hard, computationally hard. Factoring here should be computationally hard, right? So that is the sequence of works by these people. So in any case, cryptography, we love mathematics. In fact, a lot of us are sort of mathematicians masquerading as people doing something relevant to practice. And I suppose, is it recorded? Oh, maybe I shouldn't have said that. Okay, well, never mind. Everybody knows anyway. It doesn't matter. Okay, so we used problems from sort of a variety of fields, number theory, factoring, for example. Theory of elliptic curves gives us sort of very hard problems that you can use to design crypto systems, combinatorics, and so on and so forth. And all these works really resulted in systems that we use today. So when we communicate over the internet, we use one of these systems, and each of these works won a Turing Award, which is our equivalent of the Nobel Prize in computer science. So I think the density of Turing Awards in cryptography is such that your a priori probability of winning a Turing Award is pretty good if you do cryptography, I think. But okay, who cares? Yeah, so these systems are used. So what I want to tell you about is a way to use a new mathematical object, which is lattices that we saw already, to build crypto systems. In fact, we'll use it to build crypto systems with the sort of functionality that we couldn't achieve before, sort of never before sort of achievable sort of functionality. I'll describe what that means in a minute.
That's not a the algebra refers to very like a one sentence.
What does this refer to? So it's sort of algebra and, okay, so one example of using algebra to do this is to use systems of multivariate polynomial equations, right? So, if I give you a random system of equations, it's computation over a finite field, it's hard to solve it. In fact, in the worst case, it's NP complete, and so on, right? You can use that to actually build crypto systems. And that's what I mean. Another example is a proposal by Gowers, which I was telling Jayakumar earlier today, which uses sort of iterated functions. You can use that, Tim Gowers, right? He did cryptography without actually knowing that he was doing cryptography. So his proposal can be used to construct one of these systems. So lots of ways to do this sort of thing. Yeah, another example is sort of using algebraic lattices. So these are sort of like ideals in a number field. You can use that as well. That's another example of algebra. So what I want to tell you about is how to use lattices, which you saw before, to do cryptography. In fact, I'll show you two different sort of things in cryptography that you can do with lattices. One that was known before, and this is a different way of doing it, and one that was just not known. How to do it with lattices, without lattices wasn't known. This is the first construction, in fact, the only known construction, more or less. Okay, so let's get into it. So, but let me take a little breather, myself as well as you. Anything that I can answer so far? Everything, more or less. Yeah, good. Okay, great. So, so these are elliptic curves defined over a finite field, because we love finite fields and we're not going to work over the reals or complex numbers. And turns out that the elliptic curves sort of define a group. So they define a set of points, right, x and y. So they should satisfy equations like, y squared equals x cubed plus ax plus b. This is some canonical form. Set of all points xy in fp squared that satisfy this is an elliptic curve. Is an elliptic curve, right? So now, quite magically, these set of points, which are just solutions to a polynomial system of equations, turn out to have a group structure. So there's a way to kind of take two of these points and add them together and get another point that also is a solution to this. So it's a group, right? And now you can do this thing called the Diffie-Hellman construction, which relies on the following problem. I take a point xy in this elliptic curve. Let's call it x0, y0, right? I give it to you. And I add, I'm sorry, okay, great. So I give you x0, y0, which is in the elliptic curve. I add x0, y0 to itself huge number of times. So let's pick a number m, and this notation means add xy to itself m times. So I give you both of these points, x0, y0, sorry. Can you find m? So this is kind of like the logarithm problem, if you think about it, right? But in an additive notation, right? So I give you x and x to the m. You should find m, right? I mean, this problem turns out to be very, very hard, and you can use that to build a crypto system. Great. So lattices, right? So let's sort of get into it. Good. So I'm going to show you two applications, like I said before. The first one is just secure communication, like we saw Alice and Bob. They have a shared key and they want to communicate with each other. And the other one is sort of a very new kind of encryption system, and we'll see that, what's the point of that and how to achieve that later. And underlying all of this, we need sort of hard problems, but hardness has nuances, right? There is NP hardness, and then there is crypto hardness, and they're very different. And what I want is crypto hardness. And what do I mean by that? Well, NP hardness really says that a problem is worst case hard. What do I mean by that? Well, for example, if I give you a graph, right? I mean, the problem of coloring the vertices of a graph so that no edge, every two endpoints of every edge are colored differently. That's the K coloring problem, if you use K colors, right? That is NP hard. Well, what does that mean it is NP hard? That means that for every algorithm that is purports to solve this problem, there exists a graph on which it fails. So it just says that there is one hard instance, right, for every algorithm. It doesn't say that most instances are, by far it doesn't say that, right? And that is not enough for cryptography, right? I mean, in cryptography, I'm trying to send you messages with a random key, but what if I have a problem where one key is hard and everything else is easy? That doesn't suffice for us. Instead, what we want is average case hardness, meaning, a large fraction of 1 minus little of 1, or like 99%, whatever fraction of the problem instances should be hard. That's what I want. Right? So there's a big gap between these two notions of hardness. We don't know how to take a problem that is worst case hard, presumably, or an NP-complete problem if you want, and turn it into an average case hard problem. We just don't know. But it so happens that, that for lattice problems, you can actually show this connection. You can take the shortest vector problem, the approximate shortest vector problem, for example. One can show that if it is hard in the worst case, meaning for some lattice, then it is hard for most lattices. So this is the type of thing that we just don't know how to show for. We have isolated examples of problems where we can show this, but definitely not in general. No, the shortest vector problem. For the shortest vector problem, the statement is that if there is I will construct a distribution over lattices. It could be Haar type distributions, but I'm going to use something different. The distribution of lattices such that if there is an algorithm that solves a random shortest vector problem for a random lattice from this distribution with probability, I don't know, 50% or something, then I can construct another algorithm that solves the shortest vector problem for every lattice.
Then it's not in.
Then it's not in B. Yeah, that's right. That's right. Even the average case problem is not in B. Exactly. That's right. So that is the type of thing that we don't know for the satisfiability problem or the coloring problem or all these things. But for lattices, we do know this. So that's very important, right? That's kind of the foundation stone. If you want to work with lattices to do cryptography, that is sort of the thing that you want.
So then you can quantify in that lattice shortest vector problem what fraction would be hard?
Yes. So we can show that for every epsilon, if there is an algorithm that solves the shortest vector, the approximate shortest vector for 1 minus epsilon, for an epsilon fraction of the lattices, then there is a polynomial in 1 over epsilon time algorithm that solves every lattice, shortest vector on every lattice. So there's a precisely quantified statement. But at the end of the day, the qualitative statement is that there's no algorithm that solves the shortest vector problem for even 0.0001% of lattices. Of course, 0.0001 is a made-up thing. It could be any constant. Okay, so that's done. And one particularly nice average case hard problem related to lattices that I would use in my constructions downstream is the following problem, which I'll describe to you. It doesn't look geometric at all. It looks very algebraic. And that's sort of what made it easy to work with lattices. It's sort of hard to build cryptosystems out of this geometry, at least for me. Once you turn it into an algebraic problem, it just becomes much, much nicer. So what is this algebraic problem? Here's the question. Pick a vector S. Okay, so it's a vector with coordinates S1, S2 up to Sn in general, right? I'll give you many random linear equations in S. So for example, I would say 5 times S1 plus 6 times S2. So that's a number. I'll write it down. Another equation, 1 times S1 plus 2 times, I'll write it down. Keep going, right? For polynomial in N many times. And I'll ask you, can you find S? Given these equations, this is all you know. Can you find S? What do you think? Has to be. I mean, we do it in our sleep, probably. This is Gaussian elimination, right? This is one way to do this, solve this problem. Okay. Okay, but I'm not happy with easy problems, like we established, right? I'm just not happy with easy problems. How do I make this problem hard? Okay, can you say again one more time? Bound the length of the solution? That's a good idea, actually. Find small solutions to a system. Very good, very good, very good. Excellent. I'm going to do kind of the dual of that in some sense, but this is a very good idea. Yes. Good. So think about the dual setting where you have fewer equations than variables. Then there are tons of solutions. I want a short solution. That is a problem called the short integer solution problem. Can also be used in cryptography, but I'm not going to quite do that. I'm going to do something slightly different. So here's one way to do it, right? So look at it. I'm giving you lots of information about these equations. That's what's letting you solve it. How about I give you less information? Now, how do I give you less information? One way to do that is to, I'm sorry to be so violent, right? Is to chop off the head. What does that mean? Well, that is a number, a binary representation of a number. Chopping off a head means forgetting the most significant bits, a few of the most significant bits, right? Another way to say it is compute all these, do all these equations, but write them mod 11 or mod some q if you want, right? That's like ignoring, mod 10 is ignoring all but the one digit, right? Mod 11 is doing roughly the same thing. I'm chopping off the head. Now, this problem is still easy because Gaussian elimination works over any finite field. In fact, any ring, actually, really. So this is still easy. Another thing I can do is I can chop off the tail. So what does that mean? I take a bit string and I ignore its least significant bits, right? So what does that roughly correspond to? That corresponds to adding some noise to the equation. So instead of giving you equal to 2, I'll add some plus minus, randomly plus minus 1, and I would tell you, well, look, this is approximately 3, approximately 7, and so on and so forth, right? So chopping off the tail. What do you think about this problem? Forget the chopping off the head. Doesn't work, as we established. Still keeps the problem easy. What about chopping off the tail? Does it make the problem hard? Isolation, in isolation. People who do statistics, and something rings a bell here. This is linear regression, really, right? I mean, that's what I'm saying. I'm giving you a linear system of equations in a few variables plus some noise. Maybe it's Gaussian noise or whatever. Figure out what the answer is. It's easy, right? Do least squares, trivial. But it turns out that if you put both of these things in place, the problem becomes insanely hard. Roughly speaking, sorry? Yeah, least squares modulo numbers, right, is very hard. If think about a least squares problem, like a linear regression problem, where I chop off the most significant bits of all the numbers. It goes haywire. Yeah, that's right. Exactly. Right, because things wrap around. So then things that are seemingly very far might actually be close modulo stuff. Yeah, just goes completely haywire. The point is that there are two different algorithms that seem to solve these two different variants of the problem. One is Gaussian elimination. The other one is least squares. Totally different. And one doesn't work for the other, and the other way around, right? So sort of, yeah, this is just an algebraic way of writing it. So you have a matrix A, which is m equations in n variables. Just put it down in a matrix. And I give you A times S, which is a secret vector, plus E. Think of it as a Gaussian noise, right? I give you A and AS plus E, find S. And this is in a regime where I give you enough equations to completely determine the solution, probabilistically. Still, the computational problem of finding S seems extremely hard. Not only that, this is called the learning with errors problem, by the way, or LWE. And I'll use LWE downstream just to abbreviate things, but at any point you don't understand the acronym, feel free to ask. Okay, so here is the punchline. The punchline is that if you can solve the learning with errors problem on the average, meaning for random matrices, random vectors, and Gaussian random noises, then you can solve approximate lattice problems. So this is a theorem of Regev, which really sort of gives us something very clean to work with to build cryptography, right? So I'm going to use LWE to build cryptography with the understanding that if you break my crypto system, you must have solved LWE. By ODED, you must have solved approximate shortest vector problems, which is very hard. Because 40 years, people haven't managed to do it. Yeah, that's the rationale. And he also showed that, assuming that LWE is hard, as in it's hard to find the solution, you can't even tell whether a bunch of noisy equations are actually noisy equations or completely random junk numbers. So this is called the decision problem of distinguishing between A times S plus E, which is noisy linear equations, and completely random numbers. You can't even tell that. Because if you could tell that, Odette says you can use it to find the secret in some algorithm. Yeah. So it seems this problem seems extremely nice. It has all these very nice properties, right? It's algebraic, yeah. And we will use it to build a crypto system now. Good, so far so good? All right, yeah.
Connection.
Good. Okay, I wanted to have a slide here. I knew someone would ask this question, but so why is LWE a lattice problem, you're asking, right? So let me, you know what, never mind. I'm gonna write here. I'm gonna write here. Someone can turn on the light, that would be much appreciated, thank you. Good, so LWE, right? So, again, the problem is given A, right, which is a matrix. Its columns are A1 up to AN, and AS plus E, find S, right? This is the problem. So I claim that A actually defines a lattice in the following way, right? So, so think about the lattice generated by all multiples of Q, right? So this is Q times the first unit vector, E may be a wrong unit vector, Q times the second unit vector. So this is like Q 0. These vectors are in the lattice. By decree, they are in the lattice. Now I'm going to add each of the columns into the lattice as well. A1, A2, etc. up to AN. Right? So this is an m-dimensional lattice. So this is an m by n matrix. Yeah, so this is an m-dimensional lattice. So now, if you take all linear combinations of the columns of this matrix modulo Q, what am I doing? I'm taking all linear combinations of A1, A2 up to AN, plus I'm shifting it by any multiple of Q, that's fine, and that's why I'm adding these guys. So these m plus n vectors together generate a lattice, and that is the lattice that I care about. Now, what is the question I'm asking about this lattice? I'm saying, well, I will take a lattice point, which is A times S, and I'm going to perturb it by Gaussian noise, decode it to the closest, that nearest lattice point. So this is the closest vector problem. That's how it is a lattice problem. Yeah, this is relatively clear. Great. So we'll use this to learning with errors to come up with an encryption system. Let's do it. Okay, so again, Alice and Bob, they have a key. I have to tell you what this key is, and there's a message, and one wants to send it to the other. Let's say for a moment that the message is a single bit. Okay, because why not? If I have to send a huge number of bits, I'll send it one bit at a time. Yeah. Okay, so what is the key going to be here? The key in my system is going to be a random vector S in ZQ to the n, the same type as comes up in LWE. Right? How do I encrypt a message? I create a noisy equation in S, a random noisy equation. A is a random vector. A in a product S is an equation, a random linear equation in S, plus E, small e is a random noisy linear equation in S, modulo Q, right? And I add it, so this is a number, right? A in a product S plus E is a number. I add the message to it, the message bit to it. Okay, that's my encryption. I claim that this is a secure encryption. And what does that mean? When someone without the knowledge of S sees this, the LWE problem, the Odette sort of version of LWE problem says that A together with A in a product S plus E looks random, looks truly random. In fact, that is true even if you see a whole sequence of A's together with noisy linear equations. So then it looks like you're adding the message to a truly random number, which gives you a truly random number with no information on the message at all, right? So that's that. That's how you encrypt. Almost. There's a space that I left there, not for no reason. Okay, so security should be clear because of what I said. How do you decrypt, right? Who decrypts? Alice decrypts, right? The other person at the other end decrypts, and she knows the key S. That's the advantage she has over the attacker. So how does she do it? She takes B and subtracts A in a product. She computes A in a product S, subtracts it from B, right? I mean, naturally. And what you get is E plus M modulo Q, right? The message, which is a bit, plus some Gaussian error modulo Q. So now the question is, what does she do? She wants the message, okay? The bit 0 or 1. But all she gets is that plus Gaussian error. So what do you do? It's unclear, right? I mean, I get some information about the message a little bit, but I don't get the message. So I need to tweak this way of encrypting slightly so that Alice can actually recover the bit. Any ideas how to do it? Combine S and D together. I want to leave this guy alone because that is how I get security. I don't want to mess with that, So they say, don't roll your crypto system at home is what they say, which is basically, if something works, leave it alone. I just want to change how I process the message and combine it with the other guy. Yes? Okay, beautiful, right? Beautiful. That's exactly what it is, right? So don't add the bit, because that is what is preventing you from sort of distinguishing between 0 plus Gaussian and 1 plus Gaussian. Multiply M by a very large number. What is a large number modulo Q? Q is not a large number because that is 0. So the largest number in some sense is Q over 2. Right? And now when you decrypt, you're going to get E plus M times Q over 2. Right? If M is 0, you get E, which is small. If M is 1, you get Q over 2 plus E, and that is separated, well separated from the 0 case. And that's how you, right? So super simple. Yeah, that's how we encrypt. Okay. Any questions so far? All right, beautiful. Oh, so the error should be small, otherwise you start sort of mixing up zeros and ones, but that's okay, actually. There are lots of things you can build. It's just a laundry list, may not mean anything. So just then, okay, all right. So now comes quantum computers, right? So you might think, okay, you already had perfectly good ways of encrypting things using elliptic curves, using factoring and so forth. Why add one more thing to the mix and make life more complicated? What's the point? It turns out that all these other ways of doing encryption can be broken in polynomial time, and in fact, quickly, if you have a quantum computer. That is the work of Peter Shor. He came up with polynomial time quantum algorithms for factoring discrete logarithms on elliptic curves and all sorts of other groups and so forth. Of course, these all, is with lots of catches here, right? You need very large scale quantum computers because these are talking about 1,000-digit numbers. And if you write down these circuits, they are 1,000 squared gates, non-error corrected gates. If you error correct them, it's 1,000 cubed gates. It's just huge, right? We don't know if they exist, right? But people seem to be spending lots of effort and time, and I suppose more importantly, money to build these things. So we get a bit antsy. Okay. So we want alternate systems, and lattices are the leading candidate for what people call quantum resistant cryptography or post-quantum cryptography, whatever it's called. In fact, more than that, NIST, actually the National Institute of Standards and Technology in the US, that's sort of like the agency that standardizes all sorts of things, starting from, I don't know, like rulers and so the mundane thing. Yeah, yeah, exactly. Meter, yeah, the notion of a meter, all the way to sort of crypto systems and more complicated things, right? So they actually ran a competition to pick a post-quantum cryptography standard, and they recently standardized a whole bunch of things. The thing I want to mention is that out of the 4, 3 are lattice-based. It really just seems like it's the top of the board. Good. Okay. These ones? Okay. Good. So I should probably decode it a little bit. So these are just names that NIST gave them. And these are roughly categorized into encryption, which you just saw, right? I mean, I want to encrypt things to you. And there, the only candidate known is a lattice-based candidate. That's the only game in town. The other 3 are digital signatures. So think about a sort of a somewhat orthogonal problem where I don't care about privacy, but I want to send a message to you through an open channel, which an adversary can modify. And when you get it, you should know that it came from me, as opposed to something that an adversary modified. So a way to do that is to sign the message, in some sense, digitally, so that an adversary cannot modify the message while coming up with a valid signature. And there are systems to do that. And in fact, in the real world, you want to do it because I can't say the adversary, oh, he just kind of looks at things and doesn't modify. I mean, he does whatever he wants, really. She does whatever she wants, right? So digital signatures are the other candidates. And there again, there are lattice-based constructions. I'm not going to tell you what they are, but there are these things. Oh, and these are just like names of the, people like to invent cute names for things. That's what. We are not nearly as good as physicists, I have to say. I mean, I have yet to hear about something that rivals black holes and string theory. Okay, so but we do what we can. All right, so this is encryption. Now let's fast forward. So encryption and secure communication has been around for centuries. In fact, thousands of millennia. The problem has been around. Let's fast forward to a problem that comes up in the 21st century. Okay, so here is the 21st century Alice, right? And she knows the notion of search engines. In fact, search engines, the notion of search engines is changing already, right? Now they're Gemini, Cloud, and ChatGPT, right? And she wants to search for something. She has a query. She wants to run it through the search engine, get the answer, right? Okay, so you could be worried that when she's sending the query over the internet to these engines, someone might actually sort of figure out what is going on there. But we know how to solve that problem. That is encryption, right? So protecting information going through the channel, no problem. We can do it. I just showed you, right? The problem is more complicated than that, because if Gemini wants to answer your question, they have to know what you're asking for, you would think, right? I mean, they have to open up the encryption. They know what you're asking for, and then they look up some sort of database and they give the answer and so forth. So they know what you're asking for. So you're protecting against the channel, but you're not protecting against the endpoint. Right? And you might be worried for all sorts of reasons, I mean, you can take my financial data, and there isn't much there. You can take my medical data, also not much there yet. But my search queries, now we are talking. Okay, so that is very private information. You can learn a lot about a person by looking at the search query. So I'm naturally worried that these companies that collect my queries, later on when a government comes and subpoenas them, what happens, right? In fact, if you look at my search queries for the past 5 years, you can implicate me of pretty much anything after the fact, right? So that doesn't seem like a good thing to happen. So you want to protect it from all parties, the endpoints and the channel. So the question is, how can Alice get the answer from the search engine without revealing her search query? Sounds bizarre, right? I mean, you ought to know what I'm asking for to answer me. Never mind. So it's called secure computation because you're protecting computation or search, right, instead of just the communication. So here comes a new notion of encryption called fully homomorphic encryption, which actually solves this problem, at least in theory, it solves this problem, right? So what do? We think about encryption as sort of like a locked box, right? You put what you want to send inside the box and lock it, send it over, right? If the other end has the key, they can open it, but nobody in the middle can open. That's how we think about encryption, right? Now, what I'm asking for is a very special type of encryption where this box reaches the other end, and the other end cannot open the box either, but they should be able to do computations on the object hidden inside the box without actually opening the box and revealing it. It's bizarre, right? I mean, one of my colleagues, Craig, actually, he had this analogy for what is happening here. He thought of this box as a box with a glove compartment attached to it, right? So, I can put my hands, sort of the thing that happens in chemistry, I suppose, labs, right? Biology labs. I can put my hands into the glove compartment and operate on what's inside without actually knowing what color it is, for example, right? So that is the sort of thing I want. I don't want to know the object inside, but I still want to do computations on it. So that's called homomorphic encryption, right? And there's this magic thing that happens that, that Gemini can do to this box, and out comes the box with the results. Right? So you transform a box that contains a search query, do a computation to it, and get the box with the results of the computation. So that's what you want. Sounds bizarre, right? Okay. Wait for one more slide. We'll get there. Okay, this is why it's called homomorphic encryption. So think about two worlds. Okay, there's a plain text world, the blue world on top, where you have numbers, let's say A, B, and C, and you want to do things with the numbers, right? For example, you want to do A plus B times C, or whatever, right? What I'm asking for is an encryption system that transforms these numbers into other numbers, E of A, E of B, and E of C. These are encryptions of A, B, and C, right? And to do this encryption, you need a key. So it's not like anybody can go from the top to the bottom. You need a key, secret key to go from the top to the bottom. And the property of this encryption that I want is that when I do the same operations on these encryptions, add them and multiply them and so forth, what I should get is an encryption of A plus B times C. So that's E is a homomorphism. It's a ring homomorphism of sorts, right? How should I think about the last operation? Plus. The plus operation. So you map a ring element here. These need to be ring elements, right? Because I need a notion of addition or multiplication. You map it to a different ring. And there's a different ring operation that I can do on these encryptions, but they mirror. Say again? It's a ring homomorphism. It's exactly a ring homomorphism, right? And that's what it is. The one difference is that I allow this map to be a randomized map. So A can map to not one encryption of A, but one of many possible encryptions of A. Any one of these encryptions of A and any one of these encryptions of B, when I add them together, should be an encryption of A plus B. That's what I want. Right? So that's a minor difference, but other than that, it is a mathematical homomorphism. Right? That's what I want. So what happens here is that these are things that I have, my numbers, my query numbers. I encrypt them and send it to Gemini. Gemini does some computation. It knows what the computation is. It does it on the ciphertext. At the end, it gets a result, but that's the encrypted actual result. And that is sent back to the user who has the secret key, and they can go backwards and get the result. This is what I want. Right? This is a homomorphic encryption. Right? This is magical, right? I mean, it's really, I mean, why would, I mean, if you think about it as a mathematical homomorphism, it sort of makes sense, right? But, it seems very, yeah.
Why did you say that this solves the problem in theory? What's that?
Good. So the question really is, so I know how to construct it, okay? I know everything here, right? But the question is, if it takes me a millisecond to compute A plus B times C, how much time does Gemini take to compute this thing? Turns out that the answer is not so pretty, okay? It may be a factor of 1,000 to 10,000 to more expensive to compute this. This is not yet used in practice at the same level as encryption, right? But it's starting to be used in practice. And the reason it's not used in practice for search, like in Gemini, is this computational cost. I mean, I'm ignoring things a little bit, but that's largely
This homomorphic version, the computational complexity be the same.
But the thing is this, right? So think about mapping a number from Z mod QZ to a matrix, right? So then the computation that I need to do to mirror A plus B is matrix addition. The computation to mirror multiplication of numbers is matrix multiplication. So that becomes much more expensive. So the rings are different, right? That's the problem. In fact, you will see in my construction exactly this happens. You can use no. I have to craft a special encryption scheme that makes this possible. So you cannot use any arbitrary encryption scheme. It won't be, if you take an arbitrary encryption scheme and try to add ciphertext, nothing happens. Okay, so I have to really carefully craft this encryption scheme. Yes.
Is homomorphic encryption and fully homomorphic?
Good. Okay. So next slide. You guys are great LLMs. Like my next slide predictors in some. Okay, good. So these folks defined this notion, homomorphic encryption, in the 70s. And F in the FHE, the fully in the FHE, means you can do any computation on the encrypted data. You can add, you can multiply. If you want to do search, that's a computation, right? You can do that. Whatever computation you want, you can mirror it. That's fully. This was a dream for many years, but there's a theorem from 2010s where we showed how to construct, in fact, a fully homomorphic encryption. You can compute whatever you want, assuming that the learning with errors problem is hard. And that's what I want to show you. In fact, I'll simplify it, but hopefully the crux of the idea is still clear. Okay, so ready? Good. All right. So I want to come up with an encryption scheme, right? Any old encryption scheme does not suffice. In fact, the one I told you before does not by itself suffice. So I want to change it a little bit. So here's my encryption scheme from before, right? So you have LWE plus the message, so forth. I'm going to make this much less efficient. I'm going to blow up this encryption. Okay, so in the following sense, my ciphertext, my encryption is going to now look like a random matrix A, S times A. So I'm going to ignore noise for a moment between friends. Hopefully that's okay. For now, I'm going to ignore the noise, explain things, and then I'll put in the noise, and you have to trust me for a moment. It all works. So there's no noise for a moment. So A and S times A. Plus, I would add the matrix, the message M, which is a bit, times the identity matrix. So the dimensions should all work out. A should be n minus 1 by n. So the whole thing is n by n, and so on. It should work out, right? So what is going on in this ciphertext? So one way to see this is that if you look at the last column of this matrix C, what does it look like? It looks like a vector A and S in a product A, right? So the last column of C, look at this. So this looks like a vector A and A in a product S plus M, right? That's what it looks like, because M times identity, the bottom right entry is just M, and this is what it looks like, right? So the last column of this bizarre ciphertext looks exactly like our old ciphertext without the error, but like I said, ignore the error for a moment, right? So I took the old ciphertext and I blew up into this giant matrix. Why did I do that? Because I want to do homomorphic encryption. Right? Okay, so this is the ciphertext.
You're not multiplying by Q by 2 because
right now, exactly. So the reason I multiplied by Q over 2 was because there was an error. Now there's no, exactly, precisely. All right. So let me write down this equation, which is what I will call the decryption equation. How do you decrypt this ciphertext? Well, I take the vector S concatenated with -1, right? Row vector, multiply by C. So that kills off this term. And what remains is M, which is a scalar, times S concatenated with -1, mod Q. Right, so this is the decryption equation. Yeah? Let me do a slight notational change. It's not super important. I don't want to carry around S concatenate -1 and so forth. Just call it T. Okay. So this is the decryption equation. So you have a secret key, you multiply it by the ciphertext. You should get the same secret key multiplied by M, which is a scalar. Okay. Does this remind you of anything? Right. Precisely. Exactly. So ciphertext matrix is a matrix for which the secret key is an eigenvector with eigenvalue M. Right? That's what it is. Now I don't want to cheat you too much. I do want to put the error back in here. And then this equation becomes an approximate equation. So this whole thing is called an approximate eigenvector encryption for this reason. Yeah? So this is the encryption system. Now I have to show you two things I claim. I have to show you how to add encrypted numbers, and I have to show you how to multiply encrypted numbers. If you can add and multiply, you can compute any polynomials. Basically, it's everything. Again, I'm cheating a little bit, but it's okay. Okay, so let's try to see. And this is very simple. It's an elementary property of eigenvectors and eigenvalues. So let's say I have two ciphertexts, C1 and C2, which both decrypt under the same key to messages M1 and M2, right? And I want to come up with another ciphertext which decrypts to M1 plus M2. How do I do it? I just add the two ciphertexts. And indeed, T is an eigenvector of the sum with eigenvalue M1 plus M2. That's homomorphic addition. In fact, I'm going back here to without errors. If I have errors, things become a little bit more complicated, but I don't quite want to get there. How do I multiply? I multiply the two matrices. So what happens, right? T is actually an eigenvector of C1 times C2 with eigenvalue M1 times M2. So this forms a ring, really, right? A set of matrices with the same eigenvector forms a ring. Yeah, it's a little proof. It's the only proof I have, I guess. Stock. So in reality, things are a bit more complicated than this because there is noise. And when I multiply, and these equations are approximate equations, and when I multiply things, the noise gets multiplied, the approximate gets multiplied by a matrix, which makes the approximate becomes less approximate, and so on and so forth. So you have to really sweat and blood and tears. You have to work hard. But once you get here, you're already quite a bit of the way through. Yeah, that's the fully homomorphic encryption. All right. So yeah, I mean, all sorts of details, but it doesn't matter. So this actually is used not at the scale of the internet at this point. This has been used for several applications. For example, you could imagine healthcare applications, right? Where a hospital system has genomic data belonging to patients. And then there is sort of people who have phenotypic data. Hospitals have phenotypic data, and so other entities have genomic data, and they want to combine it together to do genome-wide association study. This has been demonstrated with under the encryption protecting the privacy of all parties. So at the end, the parties know what SNP corresponded, had the highest value, had the highest signal, but they don't know what the data was. You can do other things. And this is actually in production for those of us who are thinking of taking a step away from theory. This system is actually being used by some governments. And lattices have enabled a whole bunch of things in cryptography. It's again a laundry list of things. And so one of the things that I keep sort of thinking about is a dream of mine is to do a grand unification of cryptography under the umbrella of lattices. Basically, lattices can enable pretty much everything in cryptography. That seems to sort of have borne out, but there's still a lot left. All right, so I have maybe 8 minutes. So this is the end of cryptography. I want to tell you a couple of different things that you can do with lattices further afield, nothing to do with cryptography. One is an application in statistics. And here our protagonist from the very first 2 slides will come back. So this is an example of the problem of Gaussian mixture learning, right? So you have a mixture of Gaussians, right? So this is Gaussian 1, Gaussian 2. A mixture of Gaussians is just a weighted convex combination of these guys. And you get many samples from the mixture, and you have to figure out what the component Gaussians are, basically. Right? So that's the mixture learning problem. So there's a story here, which I'm told is not quite accurate, but it's a good story anyway, so let me tell you. So Pearson actually, was a statistician a long time ago, last century, the one before. So he sort of studied the following problem. He was interested in crabs for some reason, and he measured the length to the shoulder length of crabs, the ratio of the two, and he wanted to sort of figure out what is going on, right? So he tried to plot this, and it wasn't quite looking like a Gaussian. It was looking sort of weird. It was looking sort of like a funky, the right tail was heavier than the left or something. So then he figured out, well, the truth might actually be that there isn't one species of crab here. There are actually 2 species of crabs. Each one generates a Gaussian, and what I'm observing is a mixture of the 2 Gaussians. Okay. Again, my statistician friends tell me that this is completely BS, but it's a good story. Good story is worth a lot, even if it's not true. All right, so that's Gaussian mixture learning, right? So this is Gaussian mixture learning. That's what we saw in the very first slide, right? What do we know about Gaussian mixture learning? It's known that information theoretically, if you don't care about efficiency or polynomial time and so forth, you just need polynomial in n. This is the dimension, g, which is the number of Gaussians, and epsilon, which is the error threshold, 1 over epsilon. Samples are sufficient to completely disentangle the Gaussians, assuming they're well separated and so forth, but yeah, more or less. But efficient algorithms seem to take runtime that grows exponentially in the number of Gaussians in the component, number of Gaussian components. So the question is it really inherent, or sort of what is going on here? So here's a theorem that we proved with my students buffer, I had to put n buffer to disambiguate the junior buffer. And we showed that assuming the hardness of lattice problems, it is hard to solve Gaussian mixture learning any better than what is currently known, more or less. Slightly cheating a little bit, but more or less. There is some exponential dependence in the number of components that's necessary, unless you also manage to somehow improve LLL, all of a sudden. So that's the application to statistics. Proof, I'm not quite.
Go back.
Yeah.
Mitra there.
Yes.
And for the same reason, this is Ankur Mitra.
Yes. Oh, as opposed to?
His mother used to be at DIFR.
Oh, really? All right. Well, I suppose I do have to correct that, don't I? I don't think I can do it online.
Go ahead, just joke. But was Aha Mitra? So A won't.
Yes, oh. That's terrible. I do have to correct it. And it's not A Moitra, it's all right, okay, good. I'm not quite going to show you the proof. Should I actually even bother? Let's show you the proof by picture, okay? That if lattice shortest vector is hard, then Gaussian learning is hard as well. Okay, so here's the lattice, right, with n short vectors. And sort of the hardness of the shortest vector problem says that it's hard to distinguish between a lattice with n short vectors from a lattice with n minus 1 short vectors, and one vector in the orthogonal direction is long. Okay, so this is using duality and so forth, but trust me on this, right? So now I'm going to show you that if you can distinguish between Gaussian and pancakes, you can also distinguish between these two different types of lattices. Okay, so how do I do that? I'm given a lattice, right? I'm going to add a Gaussian, a small Gaussian to a random point. Pick a random lattice point, whatever that means. Lattice is an infinite object, so you have to somehow define it. Random lattice point, and then you add a Gaussian to it. So what happens? This happens, this happens. It really becomes, it fills the space, basically. Because you have n short vectors, this parallel pipette is pretty small, and the Gaussians fill the space. What happens here, this is a smoothing lemma of Minkowski Regev. Now what happens to this lattice? What you get is Gaussian on n-1 dimensional hyperplanes and well-separated Gaussians. This is the pancake. So if you manage to distinguish between the two, you also manage to distinguish between the two types of lattices, QED. All right. Now, the last thing I would say is lattices and quantum computation, that there's a deep connection between lattices and quantum computation. Okay. Oh, sorry. Okay. Oh, did I mess up something? I will blame Ankur. No. No. That's all right. I mean, don't worry about it. I don't want to keep people waiting. Just let me just go through it. But thanks though. All right. So there's a question of there's a quantum computer. Apparently someone built it, right? And I gave them a hard problem, and it gave me a solution, presumed solution. How do I know that the solution is correct? Right? There are certain problems where I can easily verify a solution, like factoring, for example, right? I give you n, you run Shor's algorithm, you get p and q, I can multiply them together and verify. But that's not true for general sort of problems, arbitrary problems that quantum computers are good at. So can I take an arbitrary quantum computation, delegate an instance of it to a quantum machine, which maybe like Google or IBM or Microsoft has, but not me, right? And I'm a classical entity. Can I verify the correctness of an arbitrary quantum computation? So it turns out that the answer is yes. The answer goes through LWE, quite surprisingly. And this was discovered by Urmila Mahadev a few years ago. This really was such a, not nearly doing enough justice to it, but this is such a magical sort of protocol, uses cryptography in some very unexpected way to the problem of verifying quantum computations. This really is what got me into the field of quantum computing to begin with. So if you have a chance, you should go look it up. And that's that really, is really lots of things going on between lattices and cryptography, quantum resistance, worst case hardness I described to you. Simple, what we did was just adding and multiplying numbers. Matrices was the most complicated thing that came up. come on. Surprising capabilities, computing unencrypted data, and many connections to statistics, quantum, coding theory, more. And yeah, that's really all I had for you. Thanks. Rajesh.
So I've heard of this other, I mean, since you mentioned this brand unified theory of lattices, I've heard like this leech lattice and this Foley code and so on.
Yeah.
Does that kind of fit into this picture?
So certain algebraic lattices can be used in the place of like unstructured lattices, but leech lattice by itself is a 24-dimensional object, right? And that's definitely not good enough. I can find short vectors in a leech lattice, for example, pretty quickly. But you can tensor these lattices and so.
This code based on that.
I see. Interesting. Okay, so that's an entirely separate sort of branch of cryptography called code-based cryptography, which looks at first like lattices, but it's sort of different. It's only different because the way you add errors here is sort of like in each coordinate the error is a small number, right? So it's sort of like L1 or L2 small. In code-based cryptography, you pick a subset of coordinates and you make them totally random. You add lots of error to it, but leave the rest alone. So there's two seemingly similar ways of using codes and lattices to do cryptography, but they end up being very, very different. Nevertheless, I mean, there are sufficient similarities between these that people study, back and forth interactions between these, for sure. Indeed, yeah, yeah.
Can I ask a question from online?
Yes. Yeah. Okay. Go for it.
Yeah. So if you ask a question to AI, they can kind of guess what was the question from the answer, right? So the ring homomorphism you were talking about is only known to you, or can the AI also guess it?
The ring homomorphism is only known to me. Yeah, that's right.
Okay.
Because that is the thing that requires a secret key to.
I see. Okay. Got it.
Yeah, but in this case, they don't even get to know the answer because the answer also comes encrypted.
Right. So you have to decrypt.
But I guess the question here is, can you go back from the encrypted number to the plain text number, right? I mean, inversion is generally hard. Yeah, that's yeah. I don't expect AI to solve this problem at all. Just like I don't expect AI to. Well, okay, again, maybe I'll eat my words, but I don't expect AI to factor 5,000 digit numbers. Time will prove.
Okay, this is kind of inspired by your Caesar cipher example.
Yeah.
So suppose I don't want to, like in your example of in your part about homomorphic encryption, right?
Yeah.
Where you have this messages A, B, whatever, and then you have E of A.
Yeah.
Suppose I don't want to, is it possible to statistically, decrypt, in the sense that just like the frequency analysis, some height, some meta.
So it is possible to decrypt if you have infinite time or exponential time.
I see.
So the only way I know to decrypt it is to guess what the secret key was. And if I guessed correctly, then I decrypt it correctly. Otherwise, very unlikely that I decrypt it correctly. So I keep guessing. Okay. So that's q to the n many, 2 to the n many. It's just not feasible, right? Think of n as being 1,000. I'm told that 2 to the 1,000 is more than the number of stars in the universe. That's what we keep telling each other in between computer scientists. I just don't know if it's true, but 2 to the 1,000 is a giant number.
10 to the 300, right?
10 to the 300. Oh, okay. So that's pretty accurate. Wow. Okay. That's incredible. Okay. Oh, I see. Good. Yeah.
You were talking about like lattices could be like a unified area of cryptography.
Yeah.
So, but traditionally, like IO is considered to be somewhat of the unified thing. So, do you think it is possible to construct like IO or similar primitive?
So that was a problem that I put up there, but I removed it because it's too technical. But yes, indeed, constructing a program obfuscation scheme, which is IO, I guess, from LWE is a sure shot way to grand unified things. There might be other ways of doing it. Yeah.
Okay.
Yeah, great.
So
Right.
do you think it is possible or not?
Yes.
Okay.
Yeah.
Yes, sir.
Yeah.
Thank you.
Yeah.
What is
I wouldn't be
fully,
the one doing it necessarily, but it's possible.
what exactly does fully mean in fully homomorphic encryption?
Yeah. So homomorphic encryption by itself means that you can do computations on encrypted data, but it doesn't say what computations. So an additively homomorphic encryption says you can add encrypted numbers. A fully homomorphic encryption says you can add and multiply. In fact, you give me any arithmetic circuit, you can compute it on encrypted numbers. That's what fully means. Fully means anything you want. Cool. All right.
Hi, can I ask a question from online?
Yeah, sure.
Yeah, are there error correction algorithms of these fully homomorphic encryptions? Like, if the part of the message is corrupted, are there ways to tell that the message is corrupted?
So if you're just given an encryption, there is no way to tell that the message was had one form or the other. I mean, you can tell nothing from an encrypted message, right? Yeah, I don't know if that's what you meant.
You could put a wrapper.
You could put a wrapper of an error correcting code on top of it. Yeah, that's right. So you can take the ciphertext, you can encode it using an error correcting code, and then if there is some noise, I can tell. In fact, I can even correct it and so forth.
Supposing
Thank you.
my interpretation of
Yes.
the question, that supposing the person who has the key
Yeah.
has the key, but in the process of transmission,
Yeah.
some error is introduced.
Right, right.
So
That is the question. So the way you would do it is you would say, well, I would take the ciphertext that I just created, right? And I would use an error correcting code to further encode this guy so that when there are channel errors, I can decode it to the old ciphertext, expand it with an error correcting. Yeah, exactly. Precisely. I mean, that's not necessarily the most efficient way to do it, but that is one way to do it. So there are a bunch of more questions, it seems. I'm not sure what currently the best theoretical bottleneck. Currently the best theoretical bottleneck. Oof. Well, that's a longer answer. This is a question of Shawaiz Sheikh. I don't know, actually. I've been thinking about it. The best bottleneck is me, probably, and my intellectual limitations. I have a question and answer. Yeah, okay, I think. Okay, so I think we are covered. Yeah, questions.
Is fully homomorphic encryption or general homomorphic encryption vulnerable to side channel attacks in the perspective of adversary?
Potentially, right? So all these security claims are assuming that the adversary gets no information at all about the secret key. Now you could ask, what if they can get some partial information? You can make all these systems robust against leakage type. There's a whole field of leakage resilient cryptography that does this. But I would think of, again, this sort of like error correction as like error correction. It's a wrapper on top of what already exists. So you can do all these things. It just makes things a bit less efficient, and then you have to worry about. Yeah. Right. Thank you. Yeah. Thanks for the questions.
Many people travel here from far away. So there is a shuttle at 5:15 and another at 5:40. So,
Thanks very much.
Thank you.
Very beautiful.
Thanks for the questions.
By the way, small amendment. It is 10 to the 11 stars, 10 to the 11 galaxies. So it's about